So now we're going to talk about a chi-squared test of association. A test for association happens when we have one sample and we're looking at it for two variables. The workup of all the previous examples assumed we had separate independent samples and we were observing those samples for the outcome of one variable. All right, so when we're in the situation where we have one sample and two variables, we're going to be in the association hypothesis setting. The test for the null hypothesis that there is no association against the alternative that there is numerically equivalent for the test that we worked up already for the null hypothesis of the distributions being the same. But the hypotheses and the interpretations are different. So we're going to jump right into an example. Marketing researchers did a survey of 291 websites and determined the country of origin and location of the privacy disclosure. Results are pictured in the table. Conduct a chi-square test to see if there's evidence that country and location of privacy disclosure are associated. Now, why did I ask you to do the association hypothesis rather than the distributions being the same? Because here we have one sample of 291 websites, and we're evaluating it for two variables, the country of origin, which are my columns, and the location of the privacy disclosure on the website, which are my rows. One sample, two variables, it's a test for association. And you can think about it in the following way. Why are we doing an association hypothesis? Because it doesn't really matter what my rows and columns are. They're associated both ways. The other one was about conditional probabilities. In this case, we have one sample with two variables. We can go either way. We've got an idea of the probability that a website comes from each of those countries, and we also have a probability of where it's located, the privacy disclosure is located on a web page. So we can do either of the conditional probabilities. All right, so this time I've worked up the chi-square test in R. So that way we don't have to do the hand calculations. This is the output for the chi-square test from R, and notice that we get our chi-square value, test statistic. It's called x squared in R. It calculates the degrees of freedom to be 6. How did it get that? Because there are 4 rows and 3 columns, and 4 minus 1 is 3, and 3 minus 1 is 2, and that turns out to be 6 degrees of freedom. And then it calculated the p-value for us, which is just the right tail probability, the probability of being past 17.544 in the chi-squared distribution that's centered at 6. It came out to be 0.007479. All right, so let's do our chi-squared test with this output. So the alpha level is going to be 0.05. The hypotheses are the association hypotheses. So here, the null hypothesis is no association. So that is going to be country and location of disclosure are not associated. And the alternative is that country and location of disclosure are associated. So the null hypothesis here is kind of like association equals 0. So I know it's a little bit different because it's in words, and it doesn't have that equal sign in it, but you can think of it like that. No association is association equals 0. So the null is always no association, and the alternative is that they are associated. Something is going on. So step 3 is getting our test statistic, but we've already got it calculated, and it's 17.544. And our p-value is 0.007479. Our p is definitely less than our alpha, so we reject the null hypothesis. And there is significant evidence at the alpha equals 0.05 level to conclude country and location of privacy disclosure are associated. Remember that we're getting evidence for our alternative. So the alternative is that they are associated. All right. So now we're going to go into the chi-squared goodness of fit test. So Pearson's original idea was to use the chi-squared statistic to assess the divergence in the O's against a modeled value for the expecteds. Any model could be proposed in this way, not just for R by C tables. In this sense, the chi-squared test statistic measures the goodness of fit of the model for the expecteds. So we'll use the usual chi-squared statistic that we used in analysis of contingency tables with intuitive expected counts. We're going to do an example in just a second. And the degrees of freedom here are going to be the number of categories in your model minus 1. So there's no contingency table here. It's just the number of categories minus 1. The hypotheses for a goodness of fit are, the null is that the model fits, nothing's going on. The alternative is that the model doesn't fit, something's going on. Something's different from our proposed model. An example, a manager of a telemarketing company thinks some of the representatives are performing differently than others, even though they all have the same script which outlines the sales speech. So the manager records the number of new customers for each of 8 telephone representatives. So we've got operators 1 through 8, and we've got the numbers of customers the new customers that they have brought in. And we want to conduct a chi-squared goodness of fit test. All right, so first we've got to figure out what our hypothesis is. Okay, so the alpha level we'll assume is 0.05. The null hypothesis is that the model fits. And what's our model here? That they all perform equally, right? So the manager is going to assume they all perform equally until she finds evidence otherwise. So we can just say model fits, and the alternative is that the model does not fit. But we can go ahead and specify what our model is, so it'll help us when we do our interpretation. All right, so the model fits, and that is that the reps are performing equally. Okay, step 3 is getting our test statistic. So here we've got to compute our expected counts and our chi-squared statistic. So we said it was intuitive expected counts. So how are we going to figure out how many new customers we'd expect each rep to bring in? If they were all bringing in equal, they were performing equally as well. When I say that, it should start to make some sense. We need to figure out how many customers they all brought in and assume that they're each going to bring in 1/8 of those customers. All right, so how many customers in total? If you add up the numbers 11, 17, 9, 12, 19, 18, 13, and 21, you're going to get 120. So 120 customers were brought in. If they're all performing equally well, they should each bring in 120 divided by 8, which is 15. So the expected count for each of these cells is 15, and that's the total, 120 divided by 8. And we can calculate our chi-squared test statistic just like we did before. So our chi-squared test statistic is calculated the same way we did before. So it's going to be 11 minus 15 squared divided by 15 plus 17 minus 15 squared divided by 15, etc. until you get to the last cell, 21 minus 15 squared divided by 15. And you should get 8.6667. Now, how do we get our p-value here? Well, we need to get the right tail area of the chi-squared distribution. We need to look at the area to the right of 8.667. That's going to be our p-value. And what are our degrees of freedom? Well, how many categories do we have here? We have 8. So the degrees of freedom are 8 minus 1, which is 7. So our p-value is 1 minus chi-squared dot dist. Our number of interest is 8.667. Our degrees of freedom are 7. And cumulative equals true. And we come out with 0.2775. Obviously our p-value is large, so our p is bigger than our alpha, and we fail to reject the null hypothesis. And we see our conclusion will be there is not significant evidence at the 5% level to conclude the reps are not performing equally. Okay, so when you fail to reject the null in the goodness of fit test, it kind of sounds like a double negative. So you'll see a lot of people interpreting in this like, you know, that the reps are performing equally. But we're going to stay away from that because we're going to stay in the parameters of strict hypothesis testing, and we're going to interpret this the same way we have all of our other tests. Here there is not significant evidence to conclude the alternative, that the reps are not performing equally.